Today we're going to look at the Chinese remainder theorem, and that's also part of modular arithmetic. And we may consider a problem where it's asked to find all numbers that if you divide by 3 you get remainder 2, if you divide by 5 you get remainder 3. So in terms of modular notation you can write it as a system. So we have two conditions. First, x must be congruent to modulo 3, and also x must be congruent 3 modulo 5. Well, it's not very difficult to find a solution, because if you look at these numbers, they give remainder 2 when divided by 3. It's not just 2, it's also 5, it's 8, it's 11, 14, etc. And similarly, these numbers, they include 3, 5, and 8 as well. And then 13, etc. No, I make a mistake there. It's 3, 8, 13, not 5. Yes? Anyhow, you can see there is one number they have in common, the 8. So 8 is one solution. And it turns out that you can have more solutions, but then you have to take steps modulo 15, because if you continue here, we have 17, 20, 23, 26, and here you have 18, and then also the 23. So here the steps are 15. So it turns out there is one solution, a unique solution modulo 15. So you can say these systems can be summarized by writing x congruent 8 modulo 15. And so there is one unique solution modulo 15, and that's actually the Chinese remainder theorem. If the numbers 3 and 5 are co-prime, then, so we can write it in general, if you have a system x congruent a modulo m1 and also x congruent b modulo m2, then as long as m1 and m2 are co-prime, that means their GCD is 1. If that's true, there is a unique solution modulo m1 times m2. Unique solution modulo m1 times m2. So in that situation was 50. Okay, it's also possible sometimes to have a system of 3 linear congruences. For example, if you have x congruent to modulo 5, x congruent 3 modulo 7, and x congruent 5 modulo 13. Notice that the numbers 5, 7 and 13 are all primes. So we will expect, based on this theorem, a unique solution modulo 5 times 7 times 13, which is 455. How to find the unique solution? Well, you can do a little trial and error. For example, look at the first two equations. You can write down the numbers 2, 7, 12, 17, 22, etc. And here we can write down 3, 10, 17, 24, etc. So the 17 have in common. So you can say for the first two equations, the congruences, I should say, the solution will be 17 modulo 35. Yes? And then we combine it with the second one, and that's a bit more work. So then these solutions, they would involve 17, 52 and 60, sorry, plus 35, 87, etc. And for the third one, it will involve 5, 18, and then adding 13 all the time. It's a bit of work, but if you just are a bit persistent, it turns out that 122 is in both rows. So 122 is a solution for all three linear congruencies, so the final solution then will be x congruent 122 modulo 5 times 7 times 13, that's 445. Okay. It turns out that also there is an interesting link to Diophantine equations, because sometimes it's a lot of work to just write down all the numbers in this congruence group, and sometimes Diophantine equations can be used. So let's look at this example. Suppose we have x congruent 6 modulo 13 and also x congruent 3 modulo 22. Notice that 13 and 22 are co-prime, so Chinese remainder theorem can be applied. And now, instead of using trial and error, we want to do it in a more systematic way. Well, based on this statement, we can say that x can be written as, let's say, 13k plus 6, because it's multiple of 13 plus 6. Similarly, based on the second one, x can be written as 22l plus 3. K and l are both integrals, of course. If you combine these two equations, you can say, therefore, 13k plus 6 must equal 22l plus 3. In other words, 13k minus 22l equals minus 3. Yes. You can also turn it around, 22l minus 30k is 3. Okay, remember what we learned about Diophantine equations. In a situation like this, 22 and 13, they have a GCD 1, so there must be at least one solution, and the solution can be found by using Euclidean algorithm and turn it around. So let's look how that works. So we start with 22 and 13. And apply Euclidean algorithm. So we first write 22, it's 1 times 13 plus 9. And then we continue the same process with 13 and 9. So 13, it's 1 times 9 plus 4. And then we repeat the process with 9 and 4. So 9, if you divide by 4, you have 2, remainder 1. And then we have 4 and 1. 4, it's 4 times 1 plus 0. So 1 is clearly the GCD. And then we can first, by the way, we're not going to solve this straight away. We'll first look for a solution for this one. 22p plus 13q is 1. And then it's relatively easy to move to that one. Because 1 is the GCD. So now, starting here, we can write 1, it's 9 minus 2 times 4. And then using this equation, the 4 can be replaced by 30 minus 9. So 1 is 9 minus 2 times 13 minus 1 times 9. In other words, this will be 9 plus 2 times 9, 3 times 9 minus 2 times 13. Well, you can see it's still correct. 27 minus 26. And then this 9 can be replaced by 22 minus 13. So we have 1 is 3 times 22 minus 13 minus 2 times 13. So in other words, 1 is 3 times 22 minus 5 times 13. Yes? And well, we're still on the right track because 66 minus 65 is 1. Okay, now let's go back to this problem. So we are looking for a situation where we have 3. Well, in this equation, if you multiply everything with 3, that's allowed. So we have 3, it's 9 times 22 minus 15 times 13. And now let's see what we are looking for. We're looking for this one. So if you take 22 times 9, so if you take L as 9, and then minus 15 times 13, so if you take K is 15, then the equation is solved. In other words, our x value can be found by taking, so if you take x to be 13 times 9 plus 6, so that's 123. That is one solution, and according to the Chinese remainder theorem, let's quickly check. That's the unique solution modulo 13 times 22, 286. So that means the full solution can be written as x is congruent 123 modulo 260 286. So this is an example that shows how Diophantine equations can be used to solve these systems of linear congruences.